Okay, in this video demonstration, I'm going to show you how to carry out a Bayesian structural equation modeling analysis using AMOS. So we're going to use a very simplistic model. Basically, we have a regression model where we have anxiety, performance goals, and mastery goals as predictors of achievement. And all of these variables are being treated as continuous. So basically, I want to start off too by mentioning that when you're running Bayesian analysis, keep in mind that there are two types of distributions that we are working from. One is called a prior distribution, which is essentially a statement of your belief about how a parameter is distributed in a population. And during Bayesian analysis, the prior belief is combined with the new data, and this yields a new distribution called the posterior distribution. So you could think about the posterior distribution as essentially your updated knowledge about the population parameter. With respect to the prior distributions, it can be based on previous research and experience. In this case, it would be considered an informative prior. So essentially, we could come into our study by assuming, having a belief that the population distribution is not zero, but some other value based on previous experience with our research and so forth. In that case, we would have an informative prior, and that could be fed into our model, and then that prior gets updated based on our new information. On the other hand, if we have little background or knowledge or experience that would inform our belief about a population parameter, then the other option is that we could start from a perspective that we know nothing, in which case we would be utilizing a non-informative or diffuse prior. So for this demonstration, we're pretty much just going to be starting from the non-informative or diffuse prior. So this is our basic model, and so when we're running our analysis, what we're going to need to do before we can start our Bayesian analysis, we need to make sure that under analysis properties right here, you make sure that under estimation that you have clicked on estimate means and intercepts. So even if it's the case where you have no missing data in your data set, you still have to click on this in order to get the Bayesian estimation facility to work. So we've done that. I've also actually clicked on standardized estimates and squared multiple correlations, some of the additional things that I typically request. So I'm going to actually go ahead and start the analysis. We actually have this little icon right here says Bayesian. I can click on that, or under Analyze, I can click on Bayesian Estimation. It's going to do the same thing. Now, first off, let me note, and I'll just let this keep running. You'll notice that at the very top, you'll see a little face with a number, and it's changing. And you can also see that all of the numbers in here are changing to a greater or lesser extent. And basically what's going on is that the estimation approach involves simulation. So we're drawing essentially, simulating repeated samples and over again and re-estimating the values within our table here. So I'm going to actually click on pause right here and just kind of note that essentially what this is called a convergence statistic. The value that you see right here, 1.001, is a convergence statistic, and you see that there's a little happy face right there. So when you first start the process, in fact, let me just restart it. I'm going to click over here and restart. You see it's unhappy, and then the numbers start, and now it starts to transition to happy face. And as the numbers get closer and closer, actually fall below 1.002, then we get a happy face that's indicating that we have convergence for our model. So as long as we have an unhappy face and the number is greater than 1.002, then the model is not converged, and so we want to keep allowing it to re-estimate until convergence is satisfied. And once it is, then we can click on pause. Otherwise, it'll just keep going on forever and ever, and we don't want to do that. So I've clicked on pause right here to stop the simulations. And so now we want to look at various components within the model. So first off, let me note that in terms of evaluating the overall model fit, in the context of Bayesian SEM, we've got a couple of things that we can look at. First, we've got the posterior predictive P. And this is used to evaluate essentially the global fit of your model. So it basically addresses the question of how well the data generated, which is simulated or replicated from the model, fits with the observed data itself, so what you've observed with your sample data. And so values that are around 0.5 are indicating really an excellent fitting model. And values that deviate further and further from that are indicating poorer and poorer fit. And these authors right here actually suggested maybe a sort of some general thresholds for moving from maintaining your model to rejecting it. That there are some reasonable thresholds which might be 0.1, 0.05, or 0.01. But obviously, as you're getting closer and closer to zero, that would certainly be an indication of worsening fit. So to evaluate the fit, what we can do is we can go up here to where it says fit measures. I'm going to click on that, and so now it's creating that for me. Basically, we had a lot of samples that were generated, and so now we have our posterior predictive P that's shown. So this is it right here, and you can see that that's indicating that we have really excellent fit. Now this down here, the DIC, that's the deviance information criteria. This is actually useful for making comparisons between different models. So by itself, just looking at it in and of itself, it doesn't tell us anything about the fit of this particular model. But if I was comparing this model to another model, then the model with the lower deviance information criteria value would be the preferred model. So at any rate, let's look at a few other things. We also have, if we want to look at the posterior distribution for each individual parameter, we can click up here where we'll click this box, and this, you can see right now we've got nothing in there. And if I want to see the posterior distribution for a parameter, I can just click right here or right here. You can see that these are all the posterior distributions for these parameters within our table. And so you can see that many of them, I mean, they look pretty normal in most cases. But you'll notice that what we have right here, you'll see it says mean and basically a standard deviation. And that's this value right here and this value right here for this first parameter estimate. So the mean, basically this is the regression slope, the average of the regression slopes across all of these simulations, and then the standard deviation as well. So essentially we can look at, we can talk, it looks very similar to what, it's basically kind of like a sampling distribution, but using kind of a simulation-based approach in this analysis. So another thing to note too is that we have the CS column, which is a convergence statistic, and so this is pertaining to each of the individual parameters. And so, again, this is sort of summarizing the overall convergence for the model, and then we have the convergence statistic for each of the parameters within the model. So obviously, as these are getting closer to 1, then that's better as well. The median is just essentially the median of the distribution, the posterior distribution for the regression coefficients. And then you'll notice over here we've got a credibility interval. And kind of going back and looking at our PowerPoint here, basically a credibility interval is interpreted as the probability that a parameter lies within a particular interval. And it is possible to talk about null hypothesis testing or utilize a form of null hypothesis testing using the credibility interval. But basically, if you're doing this, you should interpret, if let's say 0, if that's our null, if that falls within the credibility interval, then you really should be interpreting it as the null as being one of a range of credible values that the population parameter may take on. So at any rate, looking at our credibility interval right here, you can see It ranges from negative 0.134 to 0.093. So 0 certainly does fall within that interval, and that would lend credibility for the null hypothesis being true. So you'll notice that I have the 95% lower bound and upper bound. If it's a case that you've opened up AMOS and you don't see some of these things, what you can do is you can go up under the options tab, and you can see under display what you'll see are we got the mean, standard error, standard deviation, convergence statistic, median. I've clicked on the credible interval. You can also get skewness, kurtosis, minimum and maximum values, and so forth for the posterior distribution. When I first opened up the program for the credible interval, it was actually defaulting at 50%. So basically, I just raised it up to 95% right here. So, looking at our results, you can see that at least if we want to use the null hypothesis testing approach, where the null for the population parameter is 0, then we would say that the relationship between anxiety and achievement is non-significant because 0 falls within that credible interval. The relationship between mastery and achievement is positive and is significant, as 0 falls outside of that credible interval. And when we look at performance goals and achieve, you can also see that 0 falls outside of the interval, there being a negative relationship there. So at any rate, that kind of provides sort of a general first step at looking at Bayesian SEM using AMOS.